chapter 4, laws of motions, laws of motion. Okay, so starting from today, we're gonna talk about this new chapter. And then, as I explained, this is the most important chapter in this whole semester in mechanics. Okay, so and in terms of difficulty, this chapter is also probably the most difficult chapter of the whole class. As you see here, we start from 1D motion. It's kind of like a little bit of math there, and then we go to 2D motion. It's getting more complicated. You have vectors, components, and then the 2-dimensional problem. You do break down to 1-dimensional problem, and so it's getting more and more difficult. Well, in chapter 4, we talk about a lot of 2D motions as 2D problems as well. So it's going to make it also kind of complicated. But after chapter 4, actually, it's going to getting better. You know, it's going to be, I'm not saying it's going to be like become way easier, but at least it's not more difficult. It might be a little bit easier than this chapter, okay? So because, chapter 5 in energy, chapter 6 momentum, and then chapter 7, 8 in rotations, they're either easier or about same level or a little bit easier. And also, as time goes by, you get used to more and more about this kind of stuff, either the math part or the physics part. So that kind of help as well. So this chapter is probably the most, as I said, pay a lot of attention to this chapter, focus, try to spend a lot more time on this chapter, because this is the kind of the core of the whole thing. Okay, so what we're doing here, okay, remember in mechanics, we care about motion. There are two kinds of questions we can ask. One is kinematics. That's describing motion. And then dynamics. And that's explaining motion. So we're done with kinematics already in chapter 2 and 3. Now we're going to go to dynamics, which is explaining motion. So this is kind of like the question what, and this dynamics is a question of why. Well, certainly the second kind of question is more fundamental, right? And because physics care about understanding of nature, so certainly we need to develop a understanding why. So what kind of question we're trying to ask here? For example, remember this in dynamics, right? Remember we have consider the free fall motion, right? A ball dropping, falling down, right? Now we were saying there, okay, everything falls same time from same height because they're all constant acceleration, and the acceleration is 9.8 meters per second square going downward. Now the question is why? Why all the objects fall with same acceleration, right? This seems like pretty amazing, right? How could it be, right? All the objects fall at exactly same acceleration. Why, right? Or another case, we talk about 2D motions, right? We have this projectile motion. Something goes like this. It's a really nice parabola here, right? And we said there was we need to break it down to two motions, one along each direction. Along the vertical direction, it's a constant A motion. Along this direction, you have acceleration 9.8, AY 9.8 going downward. And then along the horizontal direction, the acceleration 0, meaning that it's constant velocity motion, right? Now again, the question is why? Why is constant velocity along this direction, right? Why sometimes you have a ball moving with constant velocity, an object moving constant velocity, sometimes you have an acceleration, whilst et cetera, right? All these kind of questions. So this kind of question, why, is what we want to try to answer in this dynamics. So we want to find out the reasons for all these motions, the reasons to have those kinematic quantities with certain given values, like 9.8 or 0 or whatever, right? So that's the key key problem we're trying to answer. Okay. Now the key person that answers those questions for us is called Newton. Okay. Okay, let me try to pull out one of the pages.
I would like to introduce our speaker.
Okay, sorry, this is another Zoom video I'm trying to listen. So Let me pull out this. Okay, so let me go to chapter 4 so I can use the information in this book. Chapter 4, page 88. Okay, this is close. Wait, what? Oh, part 1? No, is that it? Okay. Sorry, it's not here. Okay, let me open it, try to find it. So it's there. I'm gonna use maybe a different book here to show you guys. This seems it. No, is this it? Okay. No, this is not for our book, but I'm gonna use that. I will just use the use the picture here. So we want to okay, I want to show you just a picture of that guy. Okay, so here, Isaac Newton. Okay, he's the main guy that answered all these questions for us. Okay, he lived in the age like 1642 to 1727. So in the basically 17th century to 18th century, and he was a great guy. Okay, he was one of the greatest scientists and mathematician. Okay, or certainly physicist. I mean, some people argue he is the greatest physicist or even scientist, you know, that ever lived. Okay, now another guy that kind of famous about this is let me see if I can find his picture. Galileo Galilei. Maybe I don't. Okay, it's in the chapter 2. Okay, here. Yeah, he was actually a pioneer this work as well. He lived in the age right before Newton. Right after he died, Newton kind of get born, you know. So he lived in 16th century to 17th century, and he was considered as the founding father of modern physics and modern science. He developed this, development used this scientific method constantly and then make it like a routine for everybody else. So basically these two guys, Galileo Galilei and Isaac Newton, are the two guys uh, responsible for what we're talking about in this first couple of chapters, and especially Isaac Newton. Okay. So, and we're gonna learn about his mostly the laws of motion refer to Newton's the three laws of Newton's. Okay. Well, like first law, second law, and third law. Okay. And these are the critical thing for this chapter. Okay. So let's try to. I'll start from a simple demonstration here, and hopefully next week we're gonna do next week we'll do a lab on Newton's law as well. So let's look at my table here. Okay, I got a ball here. Okay, this one maybe let's use a better one. This one. Okay, I got a tennis ball here. Okay, now as you see here, right, there is no motion at all right now for the ball. The ball is staying at rest on my table. There's no motion, right? Now, how do I produce a motion? How do I create a motion to the ball? If I want to move the ball, I want to get the ball in motion, what do I do? Well, a simple thing I can do is I can give a push, right? See, when I move, I push the object, the ball, I apply a force, basically apply a force, the ball start to move, right? So it's starting from the rest to something in motion. So based on this very simple demonstration, you can conclude that the pushing here is critical for the motion. Well, essentially, when I push it, I give it the force to the object, right? Or I can move it all along like this. Well, I'm applying a force constantly to the ball. Certainly, this moves as well, right? So without doing anything, the ball stays there, right? So for the simple demonstration, you can see that what we can say here is I would say maybe force. Wait, sorry. Force is the reason for motion. Okay. for motions. I don't know whether this is convincing enough for you or not, but well, certainly in the real world, people didn't just do the simple demonstration and then conclude the thing. They did bunch of other observations and do all kinds of experiments, et cetera, tons of work. In the end, they realized that force is the reason for motions. So, and this is mostly due to Newton. So, and so okay, what's next? Okay, this is just something really simple to say, right? Force is reason, and if you're a fan of Star Wars, you probably already know this, right? Because force is everything, right? In Star Wars, like force is the main thing from the universe, right? You got everything, but what do we exactly? What should we do exactly? We need essentially we need to develop. Okay, normally we use F for force, okay. So the next thing is we want to develop a mathematical formula that connect this force, which is a dynamical quantity, to the kinematic quantities we had before. Because saying force is a motion essentially means that we want to make a connection between this quantity to all these previous quantities that we learned from kinematics. Okay. So how do we how do we do that? Again, we have to do a bunch of experiments, you know, to verify if there's a relation between force and displacement, or there's a relation between force and velocity, and or there's a relation between force and acceleration, or if there's a relation, what kind of relation it is, right? It requires very hard work and requires a lot of imagination, a lot of thinking, a lot of observation, and et cetera, et cetera. Okay, so, but again, let's here again do some really hand-waving arguments here for this kind of a discussion. Okay, so maybe I'll stop sharing this for a moment. So again, look at this this ball here, right? Now you have again, no force, no motion, right? When you apply force, there is a motion. Okay, but the question: do we have a direct relationship between force and the displacement of the object? Well, for at least for this one, right? If you look at this a ball, right? You apply the force. See, when the ball leaves the hand, it's still going, it's still moving, right? So there's only this force at this moment, and then after that, the force is gone while the ball is still moving, right? So, well, when the ball is moving, there's a displacement of the ball, right? Well, so from this simple demonstration, it seems like this force which produces the motion, right? Without the force, certainly this thing cannot move, but it does not have a direct, like a instantaneous relation to the displacement, because even without the force, it's still like displacement, right? Now, you can say the same for the velocity, okay? You can apply force. When the force leaves the hand, this thing's still going. So the velocity seems like does not need this force to produce, okay? What this force really does is give you a acceleration. See, in this case, this thing starts from the rest, right? By applying a force here, it starts to move. So you got a speed here, okay? So it's going through a process from zero velocity to some finite velocity. So what this force does is it gives you an acceleration, okay? Now, so from this argument, okay, again, this is not very rigorous argument. You really need to do a lot of like experiments to really show this relation. But based on this simple argument, we could say that the force here is directly related to acceleration, not to the displacement or to the velocity. So can you guys see the whiteboard again now? Yes. Okay. So what we're trying to say is like this not related to this directly or this, but it's related to this. Okay. Actually, it turns out that the relation between force and acceleration not only exists, but also exists in the simplest possible way. So it turns out that they are simply proportional to each other. So you have F equal to ma here, okay? Force equal to mass times acceleration, okay? So So as you see here, right, this toward is proportional. So there's no more simple, nothing simpler than this relation you can have for any two quantities, right? And amazingly, that's actually the relation between the force and the acceleration as verified by experiments. And amazingly, this is a simple thing that we have the simple law here governs all these kind of motions that we talk about. All this, I mean, we can use this to explain all kind of motions. Okay? This relation is called Newton's second law. Okay. And this actually is the main law of motion that we use in this chapter and in the later chapters. Okay, and that is the critical law. And this formula F equal to ma is considered to be one of the most important physics formulas, not the most important one. Okay, another one that you may heard about is E equals mc squared from Einstein. So these two formulas are considered to be like simple, but it's actually very fundamental, and it carries a lot of truth in the universe. And so this we learned this one today. We're not going to learn this one. So so we have F equal to ma. Okay. Now some of you may say that I don't agree with you because it seems like force is related with velocity. Because for example, right? Let's again go back to the screen. So if you have this ball here, right? Okay, let's take another object like here, right? Maybe let me use this one. Okay. So I have this again. It's kind of hard to see this, right? So let me use the no, sorry. Let me take off the virtual background. Okay. So suppose I have this object here. Okay. Now if I apply a force, it moves. But after the hand leave the object quickly stops, right? You may say, it seems like we do need a force to keep the velocity because without force, velocity is gone. Well, that's actually, it's a reasonable argument, but it's actually not true. The problem here is there are other forces that acting on this object. So when I push it, I give a force to the object, so the object starts to move, okay? You get an acceleration, so it starts to move with velocity. Now, after my hand leaves the object still moves a little bit because it got a velocity, but it stopped. Why? Because there's another force on the table, on the surface. It's a friction. So the friction actually stops the object eventually, okay? Now, for the ball, there's a friction as well. It's not very hard because it's rolling, but still, it's going to eventually stop, as you understand. It's not going to continuing moving forever. So this actually only justify our discussion. So there's always a force. It always take a force to get the acceleration. In this case, the second acceleration was obtained by the friction, on this. So we don't need a force to keep the object. We need a force to change to keep the object in motion. We need a force to change to create motion, to change the state of the object. Yeah. So this seems like it's a little bit trivial, a bit tricky point. And if you had a doubt, you're not alone. Okay, somebody else actually thought that force. So another guy called remember this guy Aristotle. That guy that claimed that heavy object falls to the ground first. He also said that force is related to velocity. Okay, he's saying that without a force, there wouldn't be a velocity there. Okay, well, it is not correct. Okay, so this guy basically acts as a stupid guy in our class. Each time he says something is wrong, but actually he's not that smart, stupid. Okay? He said a lot of other things that's smart. The only bad thing here in the physics turns out he was wrong in this case is because he didn't do any experiment. He was just thinking, use his brain, and figure out something like theoretically, but he never bothered doing the experiment. So he was wrong here. Okay? Now you could actually check this by yourself. For example, when you do skating, right? Skating on the ice. If you push yourself against the wall, you start to move, and then you can move pretty far, before you stop, right? Again, you stop because of friction, but you can imagine if you have a smaller and smaller friction, you're gonna go further and further away, and so you don't really need the force to keep you in motion. You need a force to start the motion. Okay, actually, we have another law here. It's called Newton's first law. Newton's first law. Okay. What this law says is it's not easy to express in the formula, so I'm going to write it in words. Okay. So when there's no force, okay, when force is 0, so the object either stays at rest.
I can't see the whiteboard.
Oh, I'm sorry. I forgot. I stopped sharing it. Sorry. Yeah, it's like when I switch back to the the screen, I forgot to share. Yeah. Here we go. So again, this is what I said. Aristotle said it was wrong. So Newton first law said when force is 0, the object stays at rest or in constant velocity motion. Again, this is a little bit hard to understand because we feel like in our life that when we don't push something, this stops. But that's actually, it's not the counter example because you stops because there's a friction. Okay, so if there's no friction, if you give a push to something, this thing gonna move forever. Okay, so this is our Newton's first law. Okay, we can actually verify this law by going to space. You know, when you're in space, there's no friction, and if you push something, you say, for example, you toss a ball out of your hand, this ball is gonna go forever. You know, flow away from you. Unfortunately, we do not have a magic school bus or something to travel to space. It's gonna cost too much for us to do that. You know, and actually, I have never been there, so I was just using my imagination here to think what's gonna happen. But there's some movies you can watch, like those movies about people like walk in space, or like some documentaries. You know, you can kind of feel that way. You know. So this is my point is like, so this is the first law. Okay, when there's no force, the object either stay at rest or moving with constant velocity. Okay, or in constant velocity motion. Okay. And so basically, this first law is basically talks about something called inertia. So we say that all objects, all matter has inertia. Inertia means that if you are in one state, you tend to stay in this state. If you're at rest, you want to stay at rest. If you're moving with constant velocity, you want to stay with constant velocity, unless there's some forces applied to you to change your state. Okay, it's the same thing like if you've been playing video games, you tend to play continuing video games, right? You sleeping on bed, you don't want to get up in the morning. It's your inertia, right? If you kind of watch YouTube, you keep watching it for forever, you know. Or if you're using social media, you're just using a cell phone, you look at a cell phone, you keep looking at it. It's called inertia. We all have inertia, you know. It takes force to change your state of motion and take effort, you know, to change your living status. I mean, inertia is not sometimes not good, you know. So the first law, in some sense, just saying that everything has inertia, you know. Well, for our application reasons, we could say the first law is a special case of the second law, because if you use the second law here, so when F equals 0, this, according to the second law, this means that the acceleration is 0, right? And when acceleration is 0, we know the object has to move in constant velocity motion. So in terms of solving problems, we do not need the first law, okay? The second law is already include the first law. So the second law is the one that we're gonna focus, pay our attention to, okay? And the first law is just something that's kind of useful. It's a simpler case, and it kind of serves as a starting point for the whole theory, but we don't really need the first law, okay? Yeah, we only need the second law, okay? Now, and then we also have the third law. Let's talk about third law, okay? Third law, okay? Well, this law talks about two objects, not one, but two objects, okay? Now, simply way to put it is called, let's say, we can say is action equals to reaction, okay? So what do we mean by that? Okay, again, let me turn off the whiteboard for a second, and then let me demonstrate this on this on the table. You know, so let's say suppose I want to punch I feel angry. I punch the table. Okay, use my fist. Okay, you can try this at home by punching a wall or something. Okay, now you can feel like when you apply force to the table applies same amount of force to you, meaning that the harder you punch the table, right, the more painful you feel on the fist. And this is an example of Newton's third law, action equal to reaction. In this case, my fist is generating an action or a force to the table, while at the same time, the table generates a force back to my fist. So that's the action and reaction. Okay. Let me start sharing the screen here before I forget. Okay. So you guys can see the screen right now, right? Okay. So basically, according to Newton's third law, you have two objects here. If the first object is exerting a force to the okay, let me use my eraser. Let's say the first object exerts a force on the second object. So it's coming from this. This is object 1, this is object 2. Let's call this force F12, okay? And then correspondingly, the second object would exert a force on the first object. This is the reaction, okay? Called F21. According to Newton's third law, these two forces are equal, okay? F12 equals F21, okay? So this is our Newton's third law, okay? Does that make sense? It seems like reasonable, right? It's pretty intuitive to have this kind of a situation, right? However, okay, let me ask you a question, okay? Regarding the third law, okay? Now you guys watch like martial arts, like for example, Taekwondo, definitely. When you do Taekwondo, you or other martial arts, you try to, I mean, in a real fight, right? You try to hit somebody, right? Like damage somebody. Now here's the thing, right? According to Newton's third law, action equal to reaction. So when you, for example, when you punch somebody in the face, right? And then based on the Newton's third law, somebody would react same amount of force on your fist, right? And according to the third law, these two forces are equal to each other, okay? It seems like, so what is the benefit of punching somebody, you know, hitting somebody? Because you exert a force on that person exerts the same amount of force on you, right? It seems like there's no benefit of doing that, but we know it's not true because intuitively we know that when you punch somebody, I mean it costs something, you know, on that person, but not much on you, right? So what is the contradiction? How do we explain this? How do we explain this contradiction? Is Newton's third law wrong or what? You know? Does that make sense? I mean, does the question make sense to you guys? Hannah, do you want to, I think I want to point you out because you teach like Taekwondo. What do you think about this, the question?
Is it talking about two objects that are both moving, or?
It doesn't matter. It doesn't matter whether they're moving or not. I mean, Newton's third law tells something really general. As far as one object exerts a force on the other object instantaneously, automatically exerts the same amount of force on the first object. So there's always action and reaction. It doesn't matter whether these two objects are moving or whatever, you know.
I don't know how someone reacts when I punch them. Usually they just, you know, like fall backwards. So I don't exactly know how this relates,
yeah.
but
yeah, it sounds really a little bit weird, right? But actually, it turns out, I mean, we all agree physics laws are all the fundamental explained to nature. When you hit somebody, they actually reacted immediately already. The force right there. But okay, let me explain this. Okay, but here's the deal. Although the force acting exerted are the same, okay. However, the part that exerting the force or feeling the force are different. Okay, see, when you punch somebody, you use a very strong part, very solid part of yourself, which is the fist, right? To attack somebody on their weak spot, right? Either maybe the throat or the face or the stomach, right? It's all like soft spots, right? So the forces exerted are the same, but the damage caused are going to be totally different. That makes sense? Let's put another example, right? Let's say you punch somebody, but that person was just holding the fist, and then you try to punch that person directly onto the fist, you know. Well, in that case, you probably wouldn't feel, you wouldn't gain much by like doing this, right? You feel pretty painful as well as that person, right? If that person is really well prepared, and then you really prepared with this fist here, right? So it actually, the forces are always equal. What is not equal is the spot the force is acting on, right? When you do martial art, when you want to attack somebody, you always use your strong part of your body, you know, either the fist or the elbow or the knee, right? And you want to put them on to your opponent's like weak spots, like soft spots, right? Like your face or stomach or neck, right? Whatever. And that's when it can work, right? And if you do not do that, you do the opposite, probably it's going to be, you're not going to be very efficient, I mean, effective in terms of doing things, right? So that's also why they want to actually, when they do like boxing, right, they normally require you to put certain gloves, or when the people, the kids doing Taekwondo, they wear all kind of protections. Well, those protections help to reduce the damage, right? Because the fist is oh yeah, go to face. Okay, so anyway, I hope this kind of joke or something help you to understand this Newton's third law a little better. And then next time, try to punch the wall. You see what I'm talking about, right? Like, why you punch the wall? You punch something like stone or something, right? But you feel definitely the damage on you is more than damage on the stone, because the stone is stronger, you know, than your fist, right? So even though the forces are again the same, it's going to cause more damage on you than the stone. So it's the same kind of idea. Okay, so I guess we're good. Okay, so we're done with this introduction of 3 laws. And then starting from next Monday, I'll talk about how to apply to what we talked about today about Newton's laws to solve problems for chapter 4. Okay, so I think that's all I want to talk about today. So I will start recording.